So once the lift has accelerated downwards, it reaches a phase where it's travelling downwards with a constant velocity. As it's travelling downwards with a constant velocity, as the velocity is constant, there's no unbalanced forces acting on the man or on the scales, and so the scales read the mass of the man as 80 kilograms. But then as he approaches the car park, the descent of the lift slows down. So it takes 2 seconds for the lift to go from travelling at 6 meters per second downwards to being at rest. If the acceleration is constant over this time period, what are the scales going to read? So in this case, we have an interesting situation. Here's the lift with the man on the scales. Now the lift is travelling downwards, but it's actually travelling downwards at a slower and slower rate. And so as it slows down travelling downwards, the acceleration is actually directed upwards. So what we're going to need to do is start by working out how much the acceleration is. We're told that initially the lift is travelling at 6 meters per second downwards, and that it takes 2 seconds for the lift to slow down to a stop. So the final velocity is 0. So we'll need to use the kinematic equations to work out what this acceleration is. So we've got v is equal to v0 plus at, and v is 0. v0 is 6.0 meters per second downwards, plus the acceleration times 2.0, and so we've got 2a is equal to 6.0 meters per second downwards, and this is a negative, and so the acceleration is equal to 6 divided by 2 downwards with a negative, which is equal to 3, and because of the negative it becomes upwards, so it's 3.0 meters per second upwards. So now we've got the acceleration, and we can just use the same method as before to calculate the normal force from the scales on the man. So he's got the normal force and the mg force acting on him, so the mass of the man times the acceleration is equal to mg plus n, and we know that this is upwards, this is downwards, and this is upwards, and so the normal force upwards is equal to a upwards minus g downwards, which is equal to m times the acceleration upwards, which was 3.0, plus, because this is a downwards, we're going to change it to an upwards, 9.8, and that gets rid of the negative sign, and so substituting in 80, so we've got 80 times 3 plus 9.8, which is 12.8, we end up with 1024 newtons upwards is the normal force provided by these scales. So he actually gets a lot heavier, so the reading on the scales is 1024 over 9.8, which is equal to 104 kilograms, and so that's a lot heavier than his normal mass, because the floor has to push up on the man to slow down his descent.